Logan, is your hand up? No. We're at Multi-Cellular, and we talk about tectonic plates, right? Can anyone tell me anything else? What else? Like, what do we do? What are some of the terms we use? What else? We talked about convection currents. We're talking about convection. So convection's if I touch something cold. We talk about convection, how the heat transfer of heat through wind or fluid. We talked about radiation. We talked about evaporation. And we said that the movement of the plates, right, is all driven by convection currents in the mantle. Yep.
A baby ocean.
A baby ocean. That's right. We talked about baby oceans, and we said, what was the stork, right, that brought those baby oceans? What was the geologic event that bore those baby oceans? Do you remember? We rifted apart. We rifted apart. And when plates rift apart, what do you call that?
A rift valley.
What's that?
A rift valley.
Oh, so a rift valley can form, but what do you call it when the plates actually pull apart? They're not coming together, they're pulling apart. Divergent, that's right, a divergent plate boundary. And we said those baby oceans are born. We also talked about convergent plates when they come together. We talked about subduction. And remember when you went underneath that person, you jumped up, and what did you have to yell on the other side?
Volcano.
Volcano! So we said those lines of volcanoes could be born if when one plate subducts another. We talked about how, let's say that Dakota, I was over here, Dakota's coming through this way, and I grab her hat as she goes through, because now that's my hat. That's my hat, Dakota.
Okay.
Does anyone remember you may not remember that word. You remember the word? Accreted terrain. Yeah, very good. Right? So we said that when one subducts the other, it might rip off and suture new material. Let's see here. We talked about continental rift, mid-ocean ridges, transform boundaries, faults, normal, reverse, slip strike, all that stuff. So what we want to do today is we're going to take that information and use it in the context of geological time, right? And if you remember, we said that geology, right, that we said earth science is a constant process of building up and breaking down. Building up and breaking down. And today, like last week, we really focused on that building up. We're going to keep focusing a little bit on that building up, but then we're going to spend a whole lot of time talking about that breaking down. And we said our essential question for the year, which we will partially answer today, was why are there sand dunes on the east side of the Saco River? Why would there be sand dunes on the east side of the Saco River? And today, we get to answer at least half of that question, which makes me happy. Yeah, what was that?
I'm not sure.
I don't know what that is.
I don't know that call.
Yeah, I was gonna say that's like a duck. Sad, cold duck. I don't know what that is. That was weird. Okay. So we are gonna walk this way a little ways. We're not gonna go super far, and we're gonna start getting into geologic timelines. So, what are we doing on time? It's 9:40 right now. And we said we don't need to worry so much about snack, right? Isn't that what you guys told me last time?
Right.
Because a lot of them, school doesn't start till 8:30. Okay. And do people have lunches today? What's
Yes.
their time frame
we
like?
have lunches.
Okay. So leaving here between 11:30 and 12?
Yes.
Okay.
Yeah.
Excellent. All right, grab your bags, and we're not going to walk
Okay.
too awful far.
I want 2 lines of perfect walkers. We're not going to be herd. 2 lines of perfect walkers. Thank you.
You get to know someone different on the walk. A little more that way.
Yeah, so you have a little bit more space in between each other. Not a breath. First, like the first person has to go through versus the last person. We were probably only like half of us that could do snowshoes, but it's good to wear. I like snowshoes. I think it's fun. So here's what we're gonna do. Well, I'll say this in a second. What I want to do now is I want to, like I said, take some of the things we've talked about yesterday and really throughout this whole semester, or past semester, through this year, start applying them in like a real world context. And we're going to do that by taking a trip through time, a trip through geological time. Now, what I'm going to do is I'm going to take a few minutes here and I'm going to set up a time scale for us to move through. And at certain points, we'll be looking at different geological events. While we do this, there's going to be two expectations from you. One of them is you should make sure you have your notebook as we go through them, because we'll be talking about kind of some of the bigger geological events that happen. And we're going to focus on kind of three major things that happened in the geology of New England. Three major things. And so one expectation is I'd like you to just take notes as we do this. And I'll make it easy. I'll let you know what you should be writing down. But the other thing is, in a few minutes, I'm going to split you up into three groups. And each group is going to be responsible for educating through reenacting one of those three major events. Now, normally, when we do skits in MESA, I like them to be silly. And there's no exception for that today, right? You can still be silly with it. But I'm going to give you a few minutes to plan these skits. And in these skits, there's going to be some vital information that you have learned this year that I would want you to showcase in that skit. And I'll meet with each group and kind of explain what I mean. So each group is going to get a card that's going to say something that happened in time. We have either done a game or an activity so far this year that represents or explains this event. So it's going to take a little bit of critical thinking skills and a little bit of recall, thinking back to what we've done kind of in the places we've been this year. It's not a test, right? So like have fun with it. But I'm going to be, you know, I want to kind of see like, can we apply those things that we've been doing? Does anyone remember when the first thing we did last week is I asked you to close your eyes and just stand there? You guys remember that? Mm-hmm. So I want to go back to that really quickly because time is really difficult for us to understand, right? Like, for example, how long do you think you've been here? 20 minutes, 40 minutes, 10 minutes, right? So even just that, right? We're like, I mean, that's a pretty wide variation, right? So we're talking about ridiculous amounts of time. Billions of years, millions of years, like ridiculous amounts of time. So we're going to try and put some of that into context, right? So why don't are the three homeroom, do we still have three homerooms? I guess I don't even know.
Yes,
yeah, we do.
It's
such a weird year. I'm like, okay. So are the
But
three
the numbers are probably
not
skewed.
represented very well?
Mm-hmm.
Yes.
Well, let's start there, and then we can kind of shove
Sure.
people. So why don't we get into our three homerooms? So let's have Louie go over by that kiosk. Let's have Barry go over by, I don't know, that there, right over there. And let's have Oliver go right over there, right by those trees right over there. This tape measure represents all of planet Earth's history. All right? So not all of time, but along this tape measure is all of the history of planet Earth. And right here at the gate, we're going to start at about 4.5 billion years ago. Right? And 4.5 billion years ago, our Earth came together and it was a big old rock. And it took quite a bit of time until, right now there's no gases in the air, there's no oxygen, there's nothing like that. So we need to travel all the way to right here before any single cell organisms show up. All right? So if that's 4.5 billion years ago, and we've moved 20 feet. Let's see if I can do the math real quick. 1/5. We moved about 1 billion years or so, roughly, before that first single cell organism shows up. There's no oxygen in the atmosphere. So a single cell organism would be like bacteria, or an amoeba, or any of the prokaryotes.
Algae?
Algae, yeah, some algae, yeah, algae. So, and some eukaryotes, I suppose, too, are also single-celled, but
They were later.
they were later. Yeah, you're on like the very edge of all of my knowledge about cellular biology. Yeah, just I said that word, and that's like, oh, that might be more than a no. So, right here, the first single-celled organism showed up. Right, all this time went by. Right here's where they show up. No oxygen. All right. We're gonna move another 35, we're gonna move down a little bit farther. So let's come down here. And right here, approximately right here, we have our first oxygen producing cells. So at the gate, our Earth started, and it took till right here until we even had oxygen on planet Earth.
How do you guys, can I just interrupt for one quick second? How do you think there could be life if there was not oxygen in the atmosphere? It was a hot, toxic Earth. It couldn't sustain you or me. So how is there able to be any life at all if there was not really an oxygen-rich atmosphere?
The guess was there was water.
Okay. But do you breathe water?
Just throw out those guesses. Sorry to get it wrong.
Sun energy? Heat?
Heat. Okay.
Didn't breathe oxygen?
What?
They didn't breathe oxygen?
They didn't breathe oxygen, so what would they breathe?
Carbon dioxide.
Okay, so we'll talk later, but they lived in these really harsh environments, and some of them still do. There are still remnants in deep sea vents and like inside of volcanoes.
And locked
There's
way
life.
down under ice, right? Aren't there ones like that are like way down under glaciers and stuff
Yeah,
like
like incredibly harsh environments. Thermophiles, they thrive in these really harsh environments.
that? All right. But we're still single-celled organisms here, right? Nothing multicellular. No plants, no animals, nothing like that.
Did they, kind of like a plant, did they take in carbon and put out oxygen?
Some of them did.
I was going to say, because that's how you could get your oxygen over.
So eventually what happened is that some of them started to do that, and it became an evolutionary advantage, right? And so that doesn't show up till right about here. And in those first multicellular things, like the first thing that you'd even look at and think, maybe that's a plant, that doesn't show up. Come on, come on.
How many years was that? Mike. Mike,
Yes.
that last place we stopped, how many years was that?
How many years ago was that? That was approximately, well, I need to do the math. I didn't do the math on these first ones. I didn't start doing the math for the next one. Give me a minute, and I'll get back to you on that. Here we go. Look back to the gate. Look to where we are, where I'm standing right now. This is where the first multicellular organisms start to appear. Right? So you're talking billions of years later that the first things that you would even consider to be a plant. I'm not even talking about animals yet. Just talking about something like that looks somewhat like a plant, like a bryophyte or something, like a moss.
The multicellular, more than one cell, makes up the organism. So it's a little more complex than what we saw way back there.
And this is roughly, I'm making this up, 3.5 billion years ago. Sorry, 2.5 billion years ago. Kind of making that up. I can do the actual math later.
Wait, this one?
Yeah, this one here. I didn't start doing the actual math till we get to our next step. We have not talked about geology yet, because as far as we're concerned, even though geological things are happening, what you would call current geological events, which are still a really long time ago, don't happen until after this point. So there's the gateway back there. Here's where the first thing that kind of looks like a plant shows up. And now, if we go right here, right here, we are standing at 750 million years ago. And between 750 million years ago and 500 million years ago, our first really big event takes place. Our first really big event takes place here. And now, you might be thinking, that seems like a pretty big range. That's a 250 million year range. It's not like, oh, 10 minutes in between. But that's how we have to kind of look at time. So, what I need is that first group, the group that had a 1 on the corner, our shallow sea group. You guys, this is our first big event. So let's have group number 1 is going to stand right over there, and everybody else come to this side of the tape measure, and we'll have our first performance. Our first big event.
550 million years ago, the shallow sea covers area. Sedimentary rock forms from compressed mud, silt, and sand.
Is that it? I-N-I-A, Rodinia. At least that's how I pronounce it. I might be saying that wrong. I don't know. Rodinia? That's what I've heard people say. Rodinia rips apart. Now, what did we just see in that example? When Rodinia rifted apart, what happened?
A baby ocean.
A baby ocean is born, and that baby ocean is called the Iapetus Ocean. Iapetus Ocean. I-E-P-U-T-U-S. Iapetus Ocean. Now, it was a little hard to see there, but at the very end, it looked like after that, as that Iapetus Ocean was getting bigger, were things falling into the ocean? Is that what I was seeing? Yeah. So, sediments and silt were falling into the ocean. Is there anyone here that can remember back to Weston's Beach and tell me what happens when those sediments fall into the ocean? Remember we talked about it goes down the Saco, and then it gets into the ocean, and then something happens to it. Can anyone remember what happens?
They compact and form sedimentary rock.
They compact and form sedimentary rock, and there's one word I want to hear. I want to drag one word out of someone's brain. They glue together.
Oh.
What's that word we use?
Cementation.
Cementation and lithification. Really good, really good. All right, so they go through lithification and cementation, and they become sedimentary rock. And so we have sedimentary rock on the bottom of the ocean, in the Iapetus Ocean. That is the first big geologic event in the current geologic history, right? We've already had billions of years of stuff happening, but that's the first big one. 750 million years ago. All right. And then from there, we're gonna travel 50 million years. You ready? We're gonna go 50 million years through time. Let's go. Hey, look at that, 50 million years. Woo! Hang on, everybody. So, roughly 50 million years ago, or sorry, 50 million years later, around 460 million years ago, around 460 million years, we have our first big modern orogeny. O-R-O-G-E-N-Y. Orogeny.
Can you say that again, Mike?
O-R-O-G-E-N-Y. Right, let me just look at it. O-R-O-G-E-N-Y. Orogeny. And it was called the Taconic Orogeny. This is kind of a minor one. This is one of our three big ones. This is kind of a minor one. Taconic, T-A-C-O-N-I-C. Taconic Orogeny, named for the Taconic Mountains in New York. And here what happened is don't worry so much about this one, but you can get that name down. But what happened is a big island arc, like an arc of basically island volcanoes came in. They subducted underneath one of the big plates, Laurentia, and a whole lot of heat and pressure happened. The Taconic Orogeny. So when Rodinia rifted apart, it split up into different plates, right? And the one we're mostly going to talk about is Laurentia, which is the North American plate. L-A-U-N. I should just look. L-A-U-R. Sorry, L-A-U-R-E-N-T-I-A. Laurentia. L-A-U-R-E-N-T-I-A. Laurentia. That's the North American plate. So this island arc kind of crashed into it, and that was the Taconic Orogeny.
Wait, what's that plate called again?
Laurentia. L-A-U-R-E-N-T-I-A. Laurentia. All right. Now, let's move to... I have to convert this. This and this are different. All right, right here. We're going to keep moving down. And right here, remember, that's the start of the Earth's time, that gate back there. Right here, we have now gotten to our second major event. And this is called the Acadian Erogeny. And this is roughly 480 million years ago. And we have a group that would have had a 2 on it, and their time was 480 million years ago.
I said 380 million years ago.
Oh, sorry. 380. 380. Sorry, my bad. 380. 380.
Okay. Yeah.
All right. Everybody on this side, that group over there. Let's see it.
180 million years ago, plates collided, and heat and pressure changed sedimentary rock into metamorphic rock.
An orogeny, did I define orogeny? Orogeny is a mountain building event caused by the folding and compression of the Earth's crust. If I didn't say that, I should specify that. It's not just any mountain building event, right? Because you have mountains built the other way. So an orogeny is a mountain building event caused by the folding and compression of the Earth's crust. $380 million years ago, give or take several million years, right? Many million years. The Acadian Erogeny happened. In that example, did anyone subduct and go under somebody else? No. It was a continental plate and a continental plate. Laurentia and Gondwana. And when they hit, they formed huge mountains, which were the White Mountains. And when the White Mountains were formed, they were approximately 15,000 feet tall. So 15,000 feet, so quite larger than they are today, right? Some estimates put them at closer to 20,000 feet. So really big mountains. And the other part, so the first thing we saw, big mountains are formed. What was the other thing that we saw that happened? What else did they showcase? What else did they do? What happened to all that sedimentary rock? Heat and pressure, and turned into heat and pressure, heat and pressure, heat and pressure, heat and pressure, and turned into metamorphic rock, right? So 750 million years ago, we had layer upon layer upon layer upon layer, right? And all that sediment dumped down and formed sedimentary rock, layer upon layer upon layer. And then 380 million years later, that ocean closed. So the Iapetus Ocean closed. The ocean closed as those plates formed huge mountains. Heat and pressure, heat and pressure, heat and pressure, heat and pressure, took all that sedimentary rock and turned it to metamorphic rock. That is that same, remember, I don't remember this, but we were standing on top of Jockey Cap months ago, and I said, if you look out, all these mountains are granite, except these higher presidentials, which are all metamorphic. The reason those higher presidential ranges are metamorphic is because of this Acadian Erogeny. All right. We're going to move to 251 million years ago. And 51 million years ago, roughly, we have a third orogeny called the Alleghenian Orogeny. And I have to look at it spelled. Alleghenian. Alleghenian. The Alleghenian Orogeny. And the Alleghenian Orogeny is basically kind of the last big push before Pangea is formed. It's the last big orogeny before Pangea, the next big supercontinent, is formed. I'm going to skip some of that part because it's not important. All right. We're now going to move up to our third big event. Our first big event was the rifting that took place up there with sediment dumping in the shallow seas of the Iapetus Ocean. Our second big event is the Acadian Orogeny. And our third big event takes place roughly 100 million years ago, which is going to place us right about here. And do we have our final group? Where's our final group? All right. How about we have final group on that side, everybody else on this side?
Okay. Ready.
Okay. 200 million years ago, continents pull apart and cause volcanic eruptions. Molten rock cools and slowly forms granite and igneous rock.
Yeah! So, right? 200 to 100 million years ago, Pangea rifts apart. As Pangea rifts apart, what is going to be born?
Ocean.
An ocean. And what ocean is still started roughly 200 million years ago and is still slowly getting bigger by 1 centimeter each year? We talked about it last week. It's like the closest ocean. Closer than the Pacific. Atlantic, yeah, Atlantic. The Atlantic Ocean, right? So the Atlantic Ocean was born. Pangea rifts apart. All that rifting causes volcanic explosions, which form the moat and Ossipee ranges, and also form places like Whitehorse and Cathedral Ledge, right? Because that magma's coming up. Some of it's cooling above ground, like those moat ranges. Some of it's cooling underground, like Cathedral Ledge and Whitehorse. At this same time, well, a little bit later, and we'll talk about this in a little bit, you also start to have these great rivers forming and starting to carve passageways through the rock. All right, and we'll talk more about that in a little bit.
Oh,
So,
yes.
what's that?
Oh, I'm just getting my snow.
Get hit by snow.
Oh, come on.
Just to put it in perspective, all right? That gate is the start of the Earth's time. Right here is where dinosaurs show up. So 65 million years ago, right about here. Right here, that's the end of our, here, hold on. Here's the end of our tape. Right there, our tape's 150 feet. So at 148.5 inches, 4 million years ago, the first thing that even looked like a human showed up. And on this measurement, let's see here. Well, half an inch would be when we do ice ages. We'll talk about that later. 0.00000.
What?
0.0000058. You don't need to write this down. Inches is when you were born. So on this tape measure, right here, if I take my fingers and open them up so I can have the tiniest amount of daylight, that's about when you were born. That is your entire life on the span from that gate to where I'm standing. So, when we talk about geologic history, we're talking about, think about everything you've done this week. Think about everything you've done this year. Think about everything you've done in your life. And that is about that much time on our scale from the gate to here. So when we talk about these geologic events, when we talk about ice ages, we don't talk about things like that are happening quickly. It wasn't like Pangea split apart and it was like, oh no, it's happening now. Like run away. Like, it's not like huge rifts are opening up, like a giant earthquake or something. It is a really, really, really slow process. So what I want to do for the time that we have remaining is I want to focus on those last inch. Not even the last inch. The last 5/100th of an inch. And focus on the glacial geology of this area because, in my opinion, it is the glacial geology that has really made this area what it is. Well, arguably the most spectacular mountain area on the East Coast, right? So it's really the glacial geology that played a role in this. So how are people feeling on their thumbs food-wise? This is like, I'm so hungry, I can't concentrate, I'm gonna pass out. And this is like, I could go for a really long time without eating. Okay. Well, that's good, because it's only 10:30. So we're gonna walk a little farther up. We're gonna play in the snow for a little while to talk about glacial geology. And then we'll get, we're actually pretty close to the Boulder already. And then in northern New England is just the remnants of the last ice age. So in a few minutes, I want you guys to break up into groups of 3 and 4. And somewhere in this area, but so you have enough space, I want you to pile up as much snow as you can and make a giant mountain out of the snow. All right? We don't have EXP groups, but do we have some
Right.
easy ways?
What if we got back into the groups that we originally just had over there?
Oh, and then split in half. Let's do that. So get into the groups that you just had, and then split in half. Mountain. I had to push the snow in from either side, and that helped build it bigger. What does that remind you of? Talk about a voice I've not heard yet today. Pushing in, making a big mountain. What does that remind you of?
Tectonic plates.
Tectonic plates, specifically convergent plates. So, 380 million years ago, during the Acadian Orogeny, right? That sea, that Atlantic Ocean was closed. Those big mountains were formed. It rifted, so then Pangea was then formed. It rifted apart, but we still had these big mountains, right? We still had those 15,000, 20,000 white mountains of New Hampshire. Well, eventually what happened, right, is you've got all these different rain and waterways, right, watersheds, and as it rains, as there's spring, as there's snow melt, that water slowly starts to carve down, down, down through erosion, right, and deposition. So it slowly starts to carve through your mountain. And what it forms by water is a narrow V-shaped valley. So rivers and streams form narrow V-shaped valleys. Oh yeah, you should grab your notebooks after this. Sorry.
Rivers and streams cause V-shaped valleys.
It slowly carves this really tight, narrow, like canyon, right? It's really tight, it's V-shaped, it's steep walls on either side, right? This narrow canyon. About 2 million years ago, which would probably make it during the Pleistocene, I think. I gotta think about that. 2 million years ago, we entered the first of 8 pulses of ice age, of ice events. And about 100,000 years ago, the Laurentide ice sheet, Laurentide, the Laurentide ice sheet began to creep down from Canada.
How many years ago was that?
100,000 years ago.
About 100,000 years ago, it began to creep down from Canada.
To this date. No, I'm only kidding. Exactly.
It reached its peak at about 10,000, oh, sorry, about 18,000 years ago or so. It reached its peak, meaning it was as far south as it possibly could. 18,000 years ago.
What was the glacier called again?
The Laurentide Glacier, and it was part of the Wisconsin glaciation period, if you really wanted to get technical. It was called the Laurentide Glacier in the northeast and central United States, and it was the Cordilleran on the Pacific Northwest. You don't need to write any of that down. That's just a fun fact for you
I
to
was like,
hear in your
I
brain.
can't remember all that fast.
So, about 18,000 years ago, this is what North America looked like. That little yellow square is about where you're standing. Everyone see that? This is what it looked like. That little yellow square is about where you're standing. The Laurentide ice sheet. The ice sheet was about a mile thick, about a mile high. So you're talking about a massive, massive piece of ice. Now, as it came down, reached its peak at about 18,000 years ago. The climate changed, it started to warm, and it started to recede. And I should mention here, like, the ice sheet didn't move, right? It's not like it was on, like, wheels and moved. It got colder and accumulated, right? So it, like, snowed a little bit more in front of it, snowed a little bit more in front of it, snowed a little bit more in front of it. And it grew that way. And when it retreated, it, like, the front part melted as it went back, right? So it didn't, like, move. And again, it's over a long period of time, right? So people weren't like, oh no, the glacier, it's coming, run! Didn't happen. Now, we have these narrow V-shaped valleys from rivers, right? Like this stick. Well, now, instead of that narrow river coming through, we saw the narrow river there, but in addition to this narrow river, you now had a big glacier that came through. And that big glacier came through, and it turned that V-shaped valley into a U-shaped valley. So I don't know if you can, if you're at the right angle, there's probably only Dakota and you guys right here that can actually see this, but you can see that it went from that narrow canyon to a big, wide U-shaped valley. And a U-shaped valley is a valley carved by a glacier. A U-shaped valley is a valley carved by a glacier. So, let's just think about this for a minute. If you have a mile thick of ice pushing through a spot, what do you think that's going to do to the ground around it? And anything in its way? What do you think that could possibly do? Compact it, crush it, and move it. So, let's just say that this cone here, right, is all stuff, like all just part of the land, as this glacier moves through. As it moves, some video, yeah, I gotta get an action shot in there. As it moves, it's getting picked up by the glacier and pushed forward. And then the glacier retreats, right? So imagine if I'm pushing snow with my hand and I'm the glacier, look at that, it pushes all that snow, then it retreats, and you have all this stuff left over, right? And what that's called, all that rubble that's left over, it's called a moraine. A moraine.
M-O-R. 2 R's, 1 R. M-O-R-A-I-N-E.
Yeah, 1 R. M-O-R-A-I-N-E. A moraine. And a moraine is rocks and sediment deposited by a glacier that form a ridge. So rocks and sediment deposited by a glacier that form a ridge. So in that example, as that glacier moved forward and stopped, like as it moves forward and stops like that, anything right here at that southern edge, at the end of the glacier, that's called the terminal moraine. And any rubble that builds up on the side, it's called the lateral moraine. And you can still see the terminal moraine of the Laurentide ice sheet. So remember, the ice sheet comes down, it pushes all those rocks. All those rocks are like collected at the end. You can still see that. And that is Martha's Vineyard, Cape Cod, and Long Island. So has anyone ever seen a map of Massachusetts or of New England? You know how there's that weird part of Massachusetts? There's a lot of weird parts of Massachusetts. Sick burn, Massachusetts. But, you know there's like that weird hook that's called the Cape? That weird hook is the terminal moraine of the glacier. The reason there are rocks out there in the middle of the ocean is because those were rocks picked up and pushed by the glacier. And then when the glacier retreated, those rocks stayed there and eventually got colonized with plants.
What's the side part of
The lateral moraine. Terminal is the end and lateral is the sides. So here's what I want you to do. I want you to go back to your mountain and I want you to create a V-shaped valley. I then want you to find like some little sticks, maybe not pine cones, it's full of sap. Bunch of little sticks, drop them in that V-shaped valley, and then push your hand through as if you were the glacier going through. And just look where all those little sticks end up. Valley, and it pushes all this rubble up and creates lateral and a terminal moraine, right? All that rock and sediment that then stays there. Cape Cod and Long Island are the terminal moraine for the Laurentide ice sheet. Now, when you guys put like your rubble and stuff in there, did it all go straight to the end, or did some of it kind of spill out on the sides? Raise your hand if any of it spilled out on the sides. Tell people. Raise your hand if some of it just didn't make it all the way to the end. Did some of it just kind of stay where it was? Yeah. So, there's evidence of that happening with the glacier as well. First of all, if you think about it, if you were to take all those rocks and push them across the ground, what do you think is going to happen to the ground? I mean, if I took a rock right now to the sidewalk and rubbed a rock on it, what's happening to the sidewalk?
being eroded?
What's that?
Being eroded.
Yeah, it gets scratched up, right? So you can go to places in the White Mountains and in Maine and see what are called striations. S-T-R-I-A-T-I-O-N, striations.
Can you repeat that?
Striations, S-T-R-A-I-T-I-O-N, striations. Oh, no, wait, S-T-R-I-A, yeah, striations, T-I-O-N. Striations. And striations are scratches in bedrock from glacial rubble. Right? I mean, if you think about it, scratches in bedrock from glacial rubble. If you think about it, and you've got all these rocks that are on the bottom of a glacier, and it's rubbing on the ground, that's going to scratch, that's going to scratch it up, right? And what's crazy is if you find these striations, you can drop a compass on them, and they should run in a north-south direction. South-north direction. Because that's the way the glacier moved when it came down, right? So if you just see scratches on a rock, it doesn't necessarily mean that they're from a glacier, but it's possible that you can find them. There's some really famous ones around that you can, they're pretty easy hikes to. You can see, there's actually some on Elephant Head, which I think we might try and go to later this year. Now, let's see, what else did I say? Oh, someone had a great question. What happened to that river that was underneath the glacier? Well, the rivers freeze up, but as the glacier starts to melt, the rivers run again. And what you have is you have a river running under a glacier, and those rivers carry sediments under the glacier. And as those sediments fall and settle out, it forms an esker. And an esker is a long ridge of gravel, deposited by meltwater. A long ridge of gravel deposited by meltwater by a retreating glacier.
Everybody get that vocabulary term down? Everybody know how to spell it? Is it E-S-K?
E-S-K-E-R.
K-E-R.
I like that word.
In this bottom left-hand corner is this is in Waterford, Maine. That is an esker that splits that lake. You guys see that there's a strip of land that goes through that lake? That is an esker. So in that bottom left-hand corner, that's an esker. So it's that land that split the lake, right? So that was under a glacier, a whole bunch of sediment was deposited. That's an old river, right? So that's all that. And you'll find them as you walk through this area. You'll walk on a trail and all of a sudden it just goes up on a little ridge. It's steep on one side, steep on the other side. It's not railroad tracks. Doesn't really seem like it should be there. Runs in the woods for a little bit, disappears. It's an esker. So they're all over the place. All right. The other one we talked about a couple weeks ago, Roche Montagne, right? That glacial plucking. So if you think about a glacier, rides up one side of a mountain, rides up, gets heavy, and then pulls it down on the other side. Like that, and you get those steep cliffs from glacial plucking. So we talked about that one already. Finally, this is very important here. Finally, some of that material, like in my example here, some of that material that gets picked up by the glacier doesn't make it to the terminal, doesn't make it to the lateral moraines, just kind of falls out, right? So if a glacier picks up a rock and carries it and drops it somewhere else, that's called a glacial erratic.
We talked about this earlier in the year, right?
Where else did you see a glacial erratic this year?
Sabatis Mountain.
Sabatis. Well done.
So a glacially deposited rock that differs in type from the rock it is deposited on. A glacially deposited rock that differs in type from the rock that it is on. So to technically be a glacial erratic, it has to get picked up by a glacier, moved, and placed on a different rock type, right? So if it's a piece of Conway granite, gets picked up and moved 20 feet and landed on more Conway granite, not a glacial erratic. If it is a massive, massive piece of Conway granite that was picked up and deposited on Concord granite, then it would be a glacial erratic. This is where we're all going to pull it together, people. Are you ready for this? We're going to pull it all together right now. So that glacier is a mile thick. It's super heavy. It is pulverizing that rock, like pulverizing that rock. Some of that rock gets pushed all the way to the terminal moraine and becomes part of Long Island. Some of that rock spills out along the way or becomes an esker. Some of that rock gets carried in big shapes and gets deposited as glacial erratics. Some of that rock gets fully pulverized to tiny, tiny little pieces and falls out in big glacial outwashes or dumps. Why are there sand dunes in Fryeburg, Maine?
Oh my gosh!
Who wants to try and put that together? Who wants to try and tell the story? Why are there sand dunes in Fryeburg, Maine? You want to try? You're not going to be wrong.
Got a piece of it, and you can put it together.
Yeah, or if you just want to tell part of it. You want to go for it?
Sure. Sediment from a glacier got like really small pieces, got deposited, and a bunch of them happened and created sand dunes.
Yeah.
That's what I was gonna say.
So,
Exact thought.
glacial outwash. that huge glacier comes and it's pulverizing rock, right? It's smashing it, smashing it. What is sand? What is sand?
Sediment.
Tiny bits of rock.
Teeny tiny bits of rock. It pulverized all that rock. And think about it. If you're carrying all this sediment, all this rock, all this sand as you flow down to Long Island, it doesn't all make it up there, down there, right? Some of it falls out. Or, as it's retreating, 12,000 years ago, it begins to retreat, which means that the front is melting. And if you have all this sediment and sand frozen in ice, and that ice melts, it's just gonna drop right there. So, we have sand dunes in Fryeburg, Maine, due to glacial outwash. These big kind of sand dumps or sediment dumps that took place as the glacier retreated. We still have one more question, a final part to answer with that, but it's going to have to wait till the end of the year. And that is, why are they only on the east side of the Saco River? We know that it was brought there by a glacier. We know it was rock that was pulverized and then colonized, right? Like, I mean, there's not still sand dunes there. It's, white pine, oak, sandy soils. But why only on one side of the river? That's the next thing that we will answer when we get into our weather unit, which is what we'll spend the rest of the year on. For right now, though, I've been talking way too much, and we should go check out this giant rock. So let's put our notebooks away.